Hi folks, Mr. Comer. We're going to kick off our unit on electricity with a rundown on electrostatics, which is electricity at rest. Electromagnetism is one of the four fundamental forces, along with gravity and the strong and weak nuclear forces. Now, electromagnetism is many times more powerful than gravity, which may sound surprising to you. But consider this. The reason why the force of gravity can accelerate us downwards at 9.8 meters per second is because of the Earth. And the Earth is huge. It's truly massive when you compare it to little old us. Yet, as you can see from this video, two magnets that are much smaller than the Earth can repel one another against the pull of gravity and cause one of them to float. Okay, so let's go briefly down to the atomic level, okay? All right, you might recognize what I'm drawing from your chemistry classes. This is the Rutherford Bohr model of the atom. Okay, there are models that are much more accurate than the one we're currently working with here, but this one's really good at showing electrical potential and electric flow. Okay, so right here we have a helium atom. Let me just finish off the electrons here. There we go, not too bad, helium atom. Okay, we can see that it has two protons in the nucleus right here, and they're positively charged. It has two neutrons in the nucleus right here. They're neutrally charged. And then there are two electrons in the valence shell that are swirling around it, constantly moving about, and they, of course, have a negative charge. Now, the helium atom is a great example because it's stable. The helium radioactive isotopes are incredibly short-lived, like milliseconds, so very stable, very balanced. It's very non-reactive to other elements, like the rest of the noble gases. And its valence shell right here is full, which means it's not a good conductor of electricity. Okay? It can only have two in this first level electron shell, and it has those two. Okay? It's also balanced, as you can see, electrically. There's two negative charges, two positive charges, 2, -2, 0. There's no charge on the helium. Okay? Now, speaking of this valence shell, hopefully you remember a little bit from chemistry. Because of the forces at play inside of the atom, the strong force, the weak force, the electromagnetic force, the outer shell always tries to be full. And here in helium, it is full. So it's happy. Okay? Now let's take a look at copper. Here's copper. A little bit more complicated. It has 29 protons. I didn't draw them all. Don't blame me. 35 neutrons and 29 electrons in its shell. Okay? The first electron shell is full. It's got its 2. So is the second with 8. And so is the third shell with 18. But look at this final fourth shell right here. It's got this lonely little electron. Just one. Okay? This shell always wants to be full. Side note, if you're wondering why, or perhaps it wasn't properly explained in chemistry, it always wants to be full, it's actually really complicated. It involves quantum theory, it involves probability, it's a little bit above our level. You can investigate on your own, or let me know if you want more information about that. But in order for this valence shell to be full, it would need 30 more electrons. That's a lot. Or copper can just ditch this little guy, kick it out, and now it will have nothing in that fourth shell, and its outermost shell, its valence shell, will be full of 18 electrons. That's what it would prefer to do, again, because of the forces at play. It's not like the nucleus is plotting against these electrons. It's just something that happens because of the forces involved. Okay? Because of this loose electron, this little guy right here that kind of wants to dance around to other places, it is an incredibly good conductor. Okay? Any item, any material with these loose electrons will be incredibly good conductors. Copper, gold, steel, silver. On the other side, atoms with stable valence shells, like rubber or plastic, are terrible conductors. Their valence shells are already full. They don't want to give or let go of any electrons, so electricity, which is electrons moving from atom to atom, doesn't really move well through things like rubber and plastic. Fun fact, we call things that conduct electricity, of course, conductors, and we call things that insulate insulators. Those are things that are bad conductors. But for the very same reason that electricity moves between materials is the same thing that allows heat conductors and heat insulators to occur. This is why, for instance, you might have a copper-bottomed pot at your house that allows the heat from the stovetop to more easily get into the pot. On the other side, you might have something like an oven mitt, which has been rubberized in order to prevent the heat from actually getting into your hand, which is for the best. From this clip, you can get an idea for how electricity flows. A current flows as each electron breaks away from its atom's valence shell and moves along the path, or circuit, as you can see here, carrying the charge. Alright, so let's get back to electrostatics. Charge doesn't necessarily have to move or flow. What you saw above, electricity, was a charge that was moving or flowing along a circuit. But what you call static electricity is an example of it not moving or flowing. When two materials come into contact with one another, particularly in a frictive way, such as rubbing together, one might tear electrons away from the other. The one that gives up its electrons becomes positively charged. It has less electrons than it did before, so it must have more protons, positive charge. The one that takes in those electrons is taking in something that is negatively charged. It becomes negatively charged itself. Now, whether one material takes or gives electrons depends on the two materials. We call this the Triboelectric Series. What you can see here is an example of this. Materials that are higher on the list will become positive if they're rubbed against materials that are lower on the list. I will demonstrate. Thankfully, the quarantine has prevented me from getting a haircut in a long time. So here's some polyethylene packing material. It's bubble wrap. It's much lower on the series than hair. So if I rub it against my head, it will become more negative, and my hair will become more positive. Now, in electromagnetism, like repels like, and opposites attract. So if you have two negatively charged objects, they repel one another. Same thing with positively charged objects. That's why the magnet from above floated. But opposites attract one another. So my hair does this. Ooh, fun. One is negatively charged, the other is positively charged, and so they attract one another, giving me a significantly worse hair day. Right, so that brings us to what I'd like you to try today. It's a small experiment that you can do at home. Really all you need is this. You need some sort of surface. In this case, I've got a little bit of wood that I'm going to use. You can use a table. You can use your wall. Just some sort of flat, solid object that you have in your house. I suspect you have flat, solid objects. Thing number two is you're going to need some tape. Scotch tape is what I'm currently using. Really, any tape will work, okay? Here's what I want you to do. Take a piece of tape, like so. Put it onto your surface with a little bit hanging off. Great. You can see the bit of tape there. Take another piece of tape. Put it on to your surface with a little bit hanging off. Great. One more. Take a piece of tape, a little bit longer this time, and put it on top of that second piece of tape. Overlap a little bit, like you can see I did here, so that you'll be able to pull the two of them apart. Now that we have these on here, I want you to rub them into the material. Rub, 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 rub on the first piece of tape. Then peel it off. What do you do with it then? Put it someplace. Little corner of a doorway, hanging off of a table, anywhere. Just use the sticky side to stick it onto something. I'm going to stick it on to the side of my iris camera. You can actually kind of see it hanging off right there. Delightful. Don't pay attention to it. It's not important that it's there. Now, with these two pieces that you have here, do the same thing. Rub, 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 rub. Rub them into the material. Okay? Rip them off. Then, separate them from one another. What you have done is you've created three pieces of tape, all of which have different electrical potentials inside them, because they've all swapped electrons in a different way. So with these pieces of tape, I want you to try holding them near each other, and also near that other piece of tape, right? So we've got our first piece of tape, number 1, then we've got these two guys, 2 and 3. Hold 2 and 3 close to each other, hold 1 and 2, and 1 and 3 close to each other. Do not let them touch each other. Just hold them close to one another and see how they react. Also, try not to let them touch yourself. If they kind of wrap around like that, they can kind of discharge themselves. You should see a difference in the way that 1 and 2, 1 and 3, and 2 and 3 interact with one another. It's going to be subtle. It's not going to be really, really, really obvious. Depending on your tape, it might be a little bit more obvious. If you don't see any differences, try it again. Rub a little bit harder this time. Try a different surface, okay? Try it a few times. There's an art of experimentation in this, but you should see some differences, okay? What I want you to do after you've done that is write to me in this little survey that I have posted on the assignment. Tell me what you did, what you saw, in as many words as you need to do so. If you didn't see anything the first time around, again, I encourage you, try this again. Try it with a different surface, try rubbing it harder, change up some variables. After you've done that, I want you to experiment a little bit with some objects around your house. There are a lot of ones that should be pretty obvious, like for instance with something like polyethylene, okay, and human hair. There's a lot of other things that you can experiment with. You'll find that styrofoam, because it's so light and packed with air, does some interesting things in the Triboelectric Series when it's introduced to charges. You can make it hop, jump, move all sorts around. You'll find that water will react if you run a little bit of water in a stream, can react to charges. So, part 2, experiment a little bit. If you have balloons in your house, try rubbing that against your hair. Try rubbing that against the wall or some sort of fabric. All right? Here's some fabric that I've got beside me right here. If you have any PVC piping in your house, try rubbing that against your hair, against a coat, against wool. Remember, wool is sheep's hair, so it does actually react in a very similar way to our hair, even more so, in fact. You don't have to use any specific materials, just take a couple and experiment with them. Let me know what you see. You might find that some of them begin reacting in a very obvious way. If, during the winter, for instance, you ever pulled a big comforter up over your head, you might have seen the crackling little bits of electricity in the darkness. That's static electricity discharging from the fibers, right? So experiment a little bit, tell me about what you experimented with, and that's it, you're done. So that's all for today, folks. Do that experiment, finish up those questions, and send them in to me on Google Classroom. Reach out again if anybody wants to do anything like a Google Meet or Zoom on some of the work that we will be doing on positive physics with electricity and with circuits. Remember, you can either come to one of the class meetings that are once a week, towards the end of the week, or shoot me an email and I can set up another meeting some other time if you prefer. Okay? I'm going to finish off with a question one student asked me in the survey, which is, what have I been up to in Animal Crossing? Well, I've been doing science. Have a good one, everybody. Be well and be safe.